Next talk is a tag team. Arnie Mudenbau will start out talking about superconductivity above 90 Kelvin in the lutetium barium copper oxide system.
Actually, you've heard much of this earlier this evening, so I'm going to skip over that. First, I'm going to give you a general slide showing the people who have been associated with the effort in high-temperature superconductivity at Brookhaven. Preparation, characterization, magnetization, high-resolution X-ray diffraction, and Simlas is going to present some interesting results later. Neutron scattering, X-ray absorption. I'm going to turn over the microphone to John Tranquata in a minute. Photo emission, work on thin films, muon spin resonance, and theory. And we want to make sure you know that we're in the high TC business, so I'll show you this slide. We're making what we think should be lutetium, barium-2, copper-3, oxygen, something, in following Wu and Kava's preprint from AT&T Bell Labs. The X-ray diffraction patterns of our multi-phase sample show similar diffraction patterns, but the optimum heat treatment hasn't yet been established. Okay, John? Can you detach me from this? Can you get it?
Okay, I'd like to talk about some X-ray absorption measurements we've made on lanthanum, barium, and strontium copper oxide compounds. We've measured both X-ray absorption near edge structure and X-AFS. We've looked at strontium doping from 0 to 0.3 and barium doping from 0 to 0.3. Since there's not much time, this is mainly going to be an advertisement. Since there's no time to go into details, we've made accurately calibrated measurements of the copper K-edge in these materials and also in a series of reference materials. We've also looked at the lanthanum L3 and L2 edges, also the barium L3 edge. It's just to show you we've measured the X-AFS in these materials at the copper K-edge from 10 degrees to 300 degrees. So then I'll just concentrate on the conclusions we've come to from our measurements. From the copper K edge, we find that there's no shift in the edge, and it lines up with a number of other nominally copper 2+ edges. And we conclude that the copper has a 3D9 configuration for all X. People have been asking the question tonight, what's the copper valence? We would, if you want to call it a valence, we'd say it's 2+. It's the important thing is a 3D9 configuration. This doesn't agree with band structure calculations, which would suggest that half of the copper D hole goes onto the oxygen, so that copper would be 3D9 plus a half, roughly. From the lanthanum L3 edge and L2 edge near edge structure, we find an increase in the white line at the edge as a function of doping, which we attribute to an increase in the number of oxygen 2p holes with doping. I think both of these results appear to be consistent with Johnson's magnetic property measurements, that we see a localized moment on the copper and we see an itinerant band in the oxygen. And then quickly from the copper K edge, we've measured mean square fluctuations in the copper-oxygen bond length from the temperature dependence of the X-AFS. Fitting that with a simple Einstein model, we get a characteristic frequency for the copper-oxygen vibrations of 50 plus or minus 4 millivolts for all X. We don't find any variation. And this fluctuation includes, although it includes lots of other modes, but it includes the breathing modes, which supposedly would soften if electron-phonon interactions are important. So we're presently analyzing our Debye-Waller factor information to see whether we're sensitive to the Kuhn anomaly contribution calculated by Weber. At the moment, we think we are sensitive to it, and our feeling is that we aren't seeing any significant electron-phonon, any significant softening of the phonons due to electron-phonon coupling. So thank you.
Thank you. The next talk is electronic, magnetic, and optical properties of yttrium, barium, copper oxide. Professor Jim Gaines.
I'd like to acknowledge the small but hard-working OSU High TC group. We have a little over 20 people in physics alone that have devoted a lot of time to our initial studies with colleagues in several other departments. I'm going to talk about, first of all, our resistive transition, and then say quite a few words about the normal state magnetization, a few words about our superconducting state magnetization, and finally a few words about some point contact Josephson tunneling measurements. Our resistive transitions look pretty much like the ones you've seen many times tonight. If we fit straight lines to the resistance versus temperature, we find that the resistance doesn't extrapolate to zero at T equal to 0, but the transition width is very narrow, approximately 2 Kelvin, with zero resistance at about 90 Kelvin. Slightly different heat treatments on the same chemistry will in fact broaden the transition and reduce the temperature where we get zero resistance. Our samples are shown by TEM studies to be the multi-phase samples with both the green and the black phases present. If we measure the susceptibility with a Faraday balance for the yttrium samples, we see an extremely strong paramagnetic contribution showing up in the results. By contrast, there's no such paramagnetic contribution if we do the lanthanum-based susceptibility measurements. Now, if we replot the yttrium susceptibility to really showcase the Curie law result, what you see is the susceptibility plotted against 1 over T is pretty accurately Curie law up near room temperature, these points, but then there are deviations as you get near the transition region, and these deviations could be thought of as antiferromagnetic deviations, but that's certainly not the only possible explanation for those deviations. In summary, we actually can extract the density of states from these measurements, and we have to do a little bit of subtraction, but we can take away the core diamagnetic contribution, the Curie contribution, and equate that to the Bohr magneton squared times the density of states. When we do this, we get really rather large numbers for the density of states in the lanthanum-based oxides, and even larger density of states for the yttrium-based oxides. We also see no EPR signal in the lanthanum-based oxides, and do see a very strong one in the yttrium-based oxides, consistent with this paramagnetic contribution we saw. I want to show you quickly just a few hysteresis loops that we have in our superconducting state. These are field-cooled susceptibility measurements, and we get about 25% of the full minus 1 over 4 pi susceptibility on the field cooling. The hysteresis loops are interesting, and they allow us to pick off the lower critical field, HC1. I don't think you've seen loops like these tonight, but these are complete hysteresis loops going through zero field. We have those as a function of temperature right up to the transition temperature. Finally, I want to show you a point contact Josephson tunneling experiment. We made a point contact junction, as shown here down in the inset, and we had about a 25 micrometer radius tip, which we could move around over the top of the sample, and then we could vary the pressure of this tip on the flat sample. It was a niobium tip with a little bit of niobium oxide on it, and we got this very, very pretty Josephson supercurrent that you see here with about a 50 microamp critical current. If we blow up that particular characteristic, you can actually see little breaks in the slope if we look out at higher voltages, and these breaks in the slope are in fact characteristic of some phase slip setters. Okay.
Thank you, Jim. These papers are open for discussion now. Yes. Mm-hmm.
Francis Thomas from AT&T. I had a question for the first speaker from Karlsruhe, Dr. Politis. I don't know if that's the right pronunciation. But you seem to show a transition at 120K, and I was wondering if that was to RU0 and what the material was.
Yes.
Can you use the microphone, please?
The materials was in the yttrium with the composition 1.2 yttrium, barium 0.8, copper 1 or Fe minus X. It was not a single phase. You have seen on the transition, it was two phase, a minimum two phase. And let me show that. This is what you mean. You see here, we have two phase. This indicated a second superconducting phase. The transition onset is 125. Even the 10 to 90 transition is 110.
You had another view graph with several oxygen pressure.
Okay.
That's not the same curve that you showed that was at 120.
Let me show. Okay. Okay, the oxygen pressure, it's over pressure from 2.5 bar of oxygen. And the sharp transition is 125, 124.
Do you have susceptibility data on that? On the 120 degree?
No, until now.
Is it reproducible?
Yes, we think so. 2 times. You know, there are not enough time to make more than 2 or 3 times the same experiment.
Oh, yes. I'm sorry. Yes. Can you use the microphone, please?
I cannot hear you, please. Can you use... I told just before, 2.5 bar over pressure.
Any other discussion? Or yes. Mm-hmm.
I had a question on the talk from the Ames group where they reported the lutetium material. I didn't hear. Did they report a transition temperature for that system?
Arnie?
Earlier this evening, they reported on it more fully.
I'm sorry, I can't hear you.
The onset temperature is 90.
90 degrees?
Yeah, in magnetization.
That's magnetization. What about
Well-
transport?
What do you mean,
The
resistance?
resistivity.
The resistance curves are not extremely accurate. here's the resistance for what it's worth. The midpoint's around 80 here, and there's a resistance here that's a little bumpy, and maybe it turns down at around 100. There's nothing shown in the magnetization, Meissner effect, which reflects this, though.
Marvin, yes. Mm-hmm.
On the 125-degree superconductor, how low was the resistivity?
Our instrumental resolutions is 10 to minus 9, 10 to minus 10 ohms. Sorry for that.
Okay, one quick question, please.
Lynn Boker from Oak Ridge. Again, on the 120 or 125 degree material, what was the temperature at which the high-pressure oxygen deal was done?
Well, it was a step from 2 times, hitting a 900 the first time, and the second time at 740.
I'm sorry, I didn't quite hear the last one.
740 the second time.
Okay, I think we'll push ahead. Neil's going to give me a respite here and take over.
We're here.
Begin with the first paper to be given by Dr. Ginsberg, specific heat and magnetic susceptibility measurements on certain compounds.
Thank you very much. I appreciate you all still being here. At the University of Illinois, we now have about 26 faculty members who are currently doing research on superconductivity. We're delighted to have ceramists, electrical engineers, metallurgists, as well as physicists. 4 of us were doing research on superconductivity before BCS. We're still there. There are a bunch of students. I don't know the students' names, so I can't list them. I know my own students, but I don't know about the other students. We have some interesting data, which I cannot talk about today because I only have a few minutes. So Myron Salomon has some good electron spin resonance data. Charlie Slichter has nuclear magnetic resonance data, and so on. So we'll just concentrate on the specific heat. I won't show our resistance and magnetic susceptibility transitions because they look just like everybody else's. I'm going to talk about the specific heat of the lanthanum barium copper oxide and lanthanum strontium copper oxide. The 2 students who did the work are Reeves and Friedman. We have NSF support, for which we are very grateful. We prepared the samples in the usual way using carbonate and oxide powders with the usual mixing, grinding, heating, pressing, sintering, and so on. We've got X-ray diffraction data which show that we have single-phase samples with the K2NIF4 structure. We've used adiabatic calorimetry. We're new to the specific heat game, but we know that we're getting the right results because we measured pure copper and got the same answer as Clayton Swenson, who is one of the most careful workers in the field. Our calorimeter is run under computer control, and I'm going to show you the data. The calorimeter was put together to do specific heat work on Chevreul phase compounds. The sensitivity poops out as you get up toward 40 degrees, and so you start to get scatter up there. But we have some pretty nice data for which we're grateful. The left-hand axis shows you the specific heat of the lanthanum strontium copper oxide. The right-hand axis shows you the specific heat of the lanthanum barium copper oxide as a function of temperature from 5 degrees on up to about 40. Now, what we did with these data were to plot them as a function of C over T as a function of T squared. We did not yet measure the specific heat in a magnetic field, but I hope to show you that we've got some very interesting conclusions from the data. Now, when you plot C over T versus T squared, it usually means you're working with a normal metal and you expect the specific heat to go as gamma T plus something proportional to T cubed. Nevertheless, we did this, and we've got something kind of interesting, namely that for both compounds, the specific heat is a linear function here at low temperature. I mean, C over T is a linear function of T squared. This indicates, according to our analysis, that the electronic specific heat is, would be the intercept here, which is about the same as the previous speaker mentioned, about 5 or so millijoules per mole degree squared in the case of the strontium compound. In the case of the barium compound, with the right-hand axis, the intercept is very small, so there's very little apparent gamma value. We interpret this intercept for the strontium compound to mean that there's probably still a little bit of the sample that's in the normal state. We take initially the T cubed part of the specific heat and assume we can extrapolate it upward in order to estimate what this lattice specific heat is at the higher temperature. Now when we do that, we get this kind of a result. The little green arrow here and this green arrow here would, for this particular value of T squared, give us the total electronic specific heat according to this construction. The purple arrow then gives us the lattice part, and we can then take the electronic part and start to think about it and analyze it. Now we assume here that we have a second order transition to the normal state, and so that the entropy at the superconducting transition temperature has to be equal to the entropy of the normal state. So if we integrate C over T dt, where C is the electronic part of the specific heat, we should get gamma T, and that gives us a value of the electronic specific heat coefficient gamma. The result of this is that the gamma values we get are about an order of magnitude too large, according to, for instance, critical field data acquired at Iowa State. They get around 5 or so millijoules per mole degrees squared. So as a result, we conclude that the linear extrapolation indicated on the previous view graph was incorrect. In other words, the lattice specific heat does not extrapolate along that straight line. Most of the specific heat you see here at these temperatures beyond which the plot is deviated from the straight line, most of that is phonon specific heat. What that indicates to us is that there are soft modes around, because the Debye model assumes a straight line relation between omega and k, and this excess specific heat that we see in the lattice would correspond to phonon modes of unusually low frequency. And you heard several theorists much earlier in the evening say that they thought there were soft modes in these materials and that they play an important part in explaining the high transition temperatures. Thank you.
Thank you very much. The next paper is to be given by Dr. Ong. Hall effect in lanthanum strontium copper oxide, implications for band structure.
I'm going to be very brief. I'll just show you the data and then discuss a little bit the implications. The work was done with my co-workers, Wang and Clayhole at Princeton, and in collaboration with Tarascon, Green, and McKinnon Belcourt. The main findings are that it's Hall-like, which is not surprising, and the density actually increases as you dope it very close to the line that you would expect from the rule that you get 1 carrier per strontium atom, until you hit the composition 0.15, where we think we're starting to see the orthorhombic to tetragonal transition, and then something mysterious happens. The Hall signal vanishes. And we believe that this, well, it drops below our level of resolution, and we think that this is an indication that the Fermi surface is undergoing a topological change, and the Hall and thermal power are sensitive to this change, whereas resistivity will not be. And I'll discuss a little bit the implications for Fermi surface induced instabilities in this system. The signal is small depending on x. For x of interest near 0.15, 0.16, the Hall signal turns out to be 10 times smaller, or 30 times smaller actually, than what you would expect from counting 1 carrier per strontium. We measured this at the magnet lab by rotating the sample in a superconducting field at 15 Tesla. And subsequently, also did it in a bit of magnet, although it's much more noisy when the field is running. These are 2 samples, and that's characteristic of the Hall signal. The background rho XX contamination turns out to be approximately twice the size of the Hall signal. And you can see that in going from 0.05 to 0.16, it scales somewhat. But then in going from 0.16 to 0.2, the signal vanishes even when you have doubled the probing current. The variation is as follows. Let me sort of lead you through this. If you had 1 hole per carat per strontium, then the density would increase linearly, and R sub h in a simple band model just decreases 1 over n, and that's what the solid line is. For the low X samples, this seems to be the rule. Then at the crossover, it rapidly decreases and drops below our level of resolution, and which is approximately about this line. Now, X-ray scattering data from Fleming and his friends, and also at Belcourt, have indicated that the tetragonal to orthorhombic distortion behaves as shown by this blue line and comes rapidly down to 0 about 0.2. So it's very tempting for us, and we do interpret it as simply a crossing of this phase diagram at 77 Kelvin. This is all taken at 77 Kelvin. We have a simple model which accounts for most of these features, and well, let me just go through it. In the orthorhombic phase, we assume that there's a gap in a 110 direction. Okay, just let me have that gap. In the x equals 0 compound, there's a complete filling of this first Brillouin zone, and so it's semiconducting-like. Now, the key point here is that when you dope it, you open up a pocket here, but the gap has to stay at the same place. I cannot have the situation where the gap follows the new Fermi surface. Otherwise, I would violate. I would deviate from this line very strongly. Okay, the gap has to stay there, and then when I cross the line, the tetragonal line, the gap disappears, and there's a rearrangement of the Fermi surface, and you get, instead of very small hole pockets, then you get very large electron-like pockets. So to sum up, my feeling is that the Hall signal rules out any destruction of a Fermi surface-driven instability between here and here. Thank you.
Thank you, Dr. Ong. The next paper is to be given by Dr. Kedison. High TC superconductivity in regions of possible compound formation in the yttrium compounds.
What I thought was a large group now looks like a small group, but this is the Northwestern crowd, and Ken Poppelmeyer is our crystal chemist, and Tom Mason is a ceramicist. Good people to have on a project like this. I'd like to show you some obligatory transition temperature resistance curves. The number 3 is going to 0, about 91 Kelvin with a couple of degree wide transition temperature, transition width. Our magnet runs out at 50 kilogauss. Our extrapolations are a megagauss like others you've heard today. Here's a susceptibility measured in yttrium barium-2 copper oxygen, showing the diamagnetic effect. This is the field cooling and zero field cooling. The lower sample is a sample cooled at zero field and then has 12 Gauss added to it. The upper one is one cooled through the transition at 12 Gauss. You've also seen these this evening. This is a magnetization curve from which we deduce an HC1 of about 600, which is somewhat higher than an earlier number, 600 Gauss, which is somewhat higher than an earlier number that I saw quoted tonight. All of that you've all seen before, and now let me try and address some careful studies we did, which hasn't been addressed too much this evening. The dots up there are all the compounds that we've studied. These are these triangles that physicists are going to have to rapidly get used to. This is the so-called 1, 2, 3 compound, the black compound, the superconductor. This is the green stuff. And we have done 2 careful slices at constant copper composition, one cutting across a possible line here and one cutting across a line here. And we see interesting things going on as you cross this line and as you cross the line, the join between the green stuff and the black stuff. You see that we've drawn these circles open here to the left of this line. So there's 1, 2, 3 points that show no diamagnetic signature whatsoever, no superconductivity as determined from diamagnetism, and then a string of black dots. Here is the normalized diamagnetic signal. There's nothing for the 3 points that would lie to the left of this, and then it drops off, and you can see the scatter is fairly minimal, so it looks like our composition control is reasonable. So some kind of join lies along here, and the phase to the left is not superconducting, the phase to the right is. This one should be superconducting right across, and by the phase rule there should be no difference between the amount of superconductor per point just to the left of this line and just to the right of this line. Unfortunately, we do see superconductivity right across there, as we should, but we do see a great big rise in the magnitude of the signal as we cross the line, which we should not see from the phase rule, if it is a perfect point compound. The ceramicist has speculated that we either have a range of solid solubility there along that line, or possibly that there is something funny going on with the oxygen stoichiometry. All we can say at this point is that it is not well behaved in crossing that line, and we'll have to do further work to try and pin down just precisely what is going on in that region of the phase diagram. Thanks.
Thank you, Dr. Kedison. Next paper is to be given by Dr. Grant. Structure of the superconducting phase in above 90 Kelvin yttrium compounds.
You'll have to give me a second to wire myself up here so I don't catch it in my beard. Here, get this. Well, thank you all for waiting. I know it's late, and I hope to make this talk worth your wait. First of all, I have to show you a foil with some names of people who have worked very, very hard in the last 2 months. These are the happy band of high-TC warriors at IBM Almaden. And we began working in this field in early January when most of us couldn't even spell perovskite. I want to spend a minute or so just running through the people and what they did. The synthesis team was led by Ed Engler, and with help from Victor Lee and Ed Nazal, they have made
well over 200 samples in the last 4 weeks. The characterization was done by Robbie Byers, Tom Shaw from Yorktown, who we've made an honorary member of Almaden for the past week or so, Grace Lim, and Rick Savoy. Robbie is the guy who did all the beautiful TEM work that I'll show you, and was the one who told us the direct route from a microprobe and TEM analysis of the original CHU starting material. Saved us a lot of matrix evaluation work. And he showed us how to separate out the green phase, and that's how we found out that the green phase was really a red herring. Measurements, Stuart Parkin did magnetometry, Jamie Kaufman helped in transport, Michael Ramirez, Jose Vasquez, and occasionally I even went into the lab. And on theory, we had a good deal of help and encouragement from Frank Herman, who kept us from getting too wild. Now, what I'm going to show you, it just doesn't do justice to Robbie's pictures. And he's here, and I urge you to try and get a hold of him so you can see what the photographs really look like. But these are really beautiful pictures and a tour de force in microscopy. Here is a picture of a single crystallite of 1, 2, 3. By the way, at the end of this story, we're going to agree pretty much with the Bell crystallography. The only thing that we won't agree with is the way they count. We like to call this 1, 2, 3. For some reason, they want to call it 2, 1, 3. But that's really going to be our only disagreement. Here we're on a 12 angstrom scale. Clearly you see the barium, yttrium, barium ordering. Convergent beam definitely shows the loss of a Muir plane. The space group is PMM2. We have put the cell horizontally in conjunction with standard crystallographic notation of having the C-axis along the two-fold axis. So there's some small distortion in this direction of the yttrium and the barium. How much, we don't know. The other thing to notice on this micrograph is this large white space in here. And our beginning thoughts were that these were oxygen vacancies in the copper basal plane, and you see here we've marked possible candidates. We really can't say anything about the oxygen vacancies in the yttrium plane. They could or could not be there according to these data. If they are there, I'm still a little concerned about how yttrium 3+ would collect enough negative charge to satisfy its valence. Perhaps it's not yttrium 3+, perhaps it's some other valence, and that should spur on some core level spectroscopy on yttrium. Okay. What we now see from Bob Haven's nice results, that this could possibly be a reconstruction going on in the copper basal plane, opening up these white space where the electron beam just pours right through, and that what we're seeing are the copper vacancies along this line, and then a spreading of the space between the barium atoms due to this reconstruction caused by oxygens in the barium plane moving toward the copper. And I think the story is beginning to look very, very pretty in that regard. Okay, just to show that we do superconductivity, here's a foil where, I don't know how well, it shows all right. Same sample, but annealed at different rates out of the furnace. This is fast cooling out of the furnace. This is slow cooled out of the furnace. You get two entirely different responses. Very percolative superconductivity for the fast annealed sample. Obviously, you're not getting oxygen equilibration. Slow cooled, it's very, very narrow. Was that the 5-minute bell?
It was.
Okay. I just have to show that we too have done one more foil. We have done a series of runs of substitutions. These are the ones that work. These are the ones that don't work. These are the large elements in the lanthanide series. We also have done alkaline earth substitutions. I don't remember seeing any of this tonight. I think this is a new result even this late in the evening. Thank you very much.
Thank you, Dr. Grant. The last paper in session 7, and we're getting close to the end now, The last paper in session 7 to be given by Dr. Moss, entitled High Resolution Synchrotron X-ray Study of the Structure of the Lanthanum Compound.
Okay. Thanks. Yes, it is indeed high-resolution synchrotron and not cyclotron. And it is a Houston-Brookhaven collaboration, and we were quite fortunate to have both the opportunity both to work with the people at Brookhaven, John Axe and Guido Yu, and Dietmar Holwein and Dave Cox, as well as the accessibility and availability of the instruments, which are truly wonderful. I will give you a feeling for how that resolution and intensity is useful, but perhaps before doing that, at least let you know what some of our conclusions are, and then you can have a look at the results in light of these conclusions. The principal conclusions are that we have a nominally single-phase material, which would be identified as a single-phase material in a normal diffraction experiment. One could push a rotating anode with double monochromators to give you much better resolution than that. But in a normal diffraction experiment, it would be nominally single-phase. But both the powder and 70-micron single crystal data that we collected shows clear evidence of phase segregation into two phases of identical structure and similar composition. And secondly, we see a transition to a slightly monoclinic structure occurring at around 150 degrees in at least the major of those two phases. And that assignment of monoclinic we believe to be a minimum assignment. In other words, it's either monoclinic or lower symmetry like triclinic. It's not orthorhombic. Well, we assume the tendency to phase separate into phases of presumably different electronic structure may be general in these solids. We've also done measurements on the lanthanum, strontium, copper, oxygen system, and that this may depend sensitively on oxygen and or thermal treatment. There's been a lot of talk this evening about the sensitivity of these materials to thermal treatment and to oxygen treatment, and we believe that the phase separation that we're talking about here is certainly one example of that. And if this phase separation exists, it's certainly a source of interfaces for those of you who like interfaces. Okay. Just to give you a feeling for the technique, I show here a typical scan. It turns out to be from the lanthanum strontium, not lanthanum barium sample, but it's a typical scan showing the pure tetragonal phase, okay, the potassium nickel fluoride phase. And consider this set, the 116107, the closely spaced peaks. And if you blow that up, you'll see that they have a profile like that. And we can improve that a bit in our own lab by having, tighter slits and better collimation and so on, and could bring that down like so. Consider now what it looks like at the synchrotron. That's that pair of reflections. There you go. And it's that kind of resolution that is so impressive and that is in fact necessary to see some of the things that we're talking about. Sorry about that. This is 0.06 full width at half maximum and 2 theta. So we're fortunate in having both the resolution and intensity. And when you have such resolution and intensity, then you can start to see the sorts of things we're talking about. For instance, here's a pair of reflections, the 200 and 211. And just consider the room temperature set for the moment. You see there's a single peak and then a shoulder on that peak. This has been least square fit now to 2 peaks, one of them centered here and one of them centered there, a major phase and a minor phase. And the same thing for 211. When we cool down, the peaks broaden and we fit them with 2 peaks split now. And we split the minor one as well, although we don't know that it's actually split. But certainly we see a broadening on cooling and a major and minor phase. Now that is a very small separation, and it is not a criticism of anybody's sample that we say that it is hard to see. It is not as if these samples were prepared and therefore have these poor second phases, but rather that we can see second phases in samples that perhaps escaped observation before. Well, fitting a whole set of the peaks, you needn't run through this table, it's just out of our paper, but fitting the whole set of peaks, when we could find a clearly defined shoulder, we have a major phase with lattice parameters here and a minor phase with lattice parameter like so. So there's 0.04 difference in the A parameter, and 0.13 in the C parameter, and a minor phase constitution of the order of 12%. We've seen as much as 20 to 30% in the strontium compounds, and samples prepared in identical ways to other people. Then I'll just show, what's the, is that?
That's that. Yes.
Oh, let me just show the broadening then, because it's important. Here is the broadening, and here's instrumental resolution, and all the peaks on cooling broaden, and these, both the 200 and 110 peaks broaden on cooling. And because both 200 and 110 broaden on cooling, we cannot have an orthorhombic transition. It must be a transition to a monoclinic phase. And the amount of distortion is quite small. So I'll just finish up with this. It's too bad that I cannot show you the single crystal data because they're beautiful. But the amount of broadening is consistent between measured and calculated. It's consistent with a monoclinic distortion, where gamma would be 90 degrees for orthorhombic. It is now 89.96, and the difference between A and B is of the order of 0.02 angstroms. So it's a very small monoclinic distortion, but it's not orthorhombic. And it is our suspicion that some of the transitions which have been identified as orthorhombic from tetragonal to orthorhombic in the substituted strontium and barium substituted phases are indeed monoclinic. We also have single crystal data which shows clearly that the shoulder that I described in the powder pattern also appears in a single crystal, and therefore it is more likely to be a thermodynamic phase than simply the result of having a powder with this particle being phase 1 and that particle being phase 2. So it seems like this phase separation is real, and while we're talking about lanthanum, strontium, and lanthanum barium, we assume that, along with others, that if the new high TC materials are part of a similar family, that such things can occur. And one point about phase separation, phase separation, this is not so much our work, but in general. The more elements you have in a compound, the more likely phase separation is to occur. Thank you.
Thank you. These 5 papers are now open for discussion. A question for any of the speakers, please. Yes.
So is it possible that those 2 phases are Wilhelm's T and T prime phase? Are you familiar with that?
No.
I think if you look back at solid state chemistry, I can't remember the exact issue. I think he describes a rotation of oxygen. It should be the same structure, with the same parameters, except that the oxygen takes a new position. And it's possible that's what you're seeing.
Conceivable. All we can tell is that they're both tetragonal with a very small difference in composition. Because the shift in lattice parameter is so small and they appear as shoulders, it's awful hard to do crystallography on the minor phase, but it certainly seems to be tetragonal and similar lattice parameters, so we call it a second tetragonal phase.
But then we have some.
You want
Because these T and T prime,
So be it.
and just the oxygens change position in one layer. And they look exactly the same to structure.
Fair enough.
Question at the first microphone, yes.
I have a question for Dr. Grant. My name's Mark DeGeer from Case Western Reserve University. Right at the end of your talk, you mentioned, I believe, some work where you had 2 different alkaline earth cations in your materials at once. If that's correct, what were your results on those?
Okay. I think you're referring to this.
Yes.
Here, okay. We did a partial substitution of calcium for barium and strontium for barium. You might think there was phase separation perhaps, but the X-ray data was very, very clean, indicated single phase. But the clincher is when we put in 50-50 strontium, calcium. All three of these alkaline earth substitutions, both complete and partial, gave a transition temperature onset in the range of 85 degrees. Now, we did try calcium alone and strontium alone, and to date that hasn't worked for us. But it may be that we have to be more careful with the annealing. Don't know.
Thank you.
Any further questions? Just before I hand the chair back to Dr. Maple, could we please have Drs. McCrone, Scherber, Martinez, Sethna, and Gompf?
Okay, we can get started with this next session. There will be a few more after this, just to let you know where we are. This is first talk is diamagnetism and other physical properties of cadmium, sulfur, chlorine. This paper is given by R.K. McCrone.
Well, this paper is probably a dramatic change in pace because I won't talk about calcium, strontium, lanthanum, copper, or oxygen. But I thought it would be interesting at a session like this to bring up another system which shows superconducting properties to indicate perhaps that this phenomenon is not confined to the perovskites and that it may be found in many materials. Before I get going, I'd just like to acknowledge the support that we have received for this work. We've been supported by AFOSR, RADCOM, ONR, and DOE. This is perhaps the sort of gist of the talk. And that is, it says that if you take cadmium sulfide, which has been very carefully doped with 0.07 weight% chlorine, and those limits are extremely tight, and you pressure quench it, and I'll explain what this is in a minute, then you see what we believe is high temperature superconductivity. But it's a little more complicated in that there is a paramagnetic state associated also. And we've been trying for a long time to answer the question why. And I have this rather loosely defined answer. The reason is that after pressure quenching, a lot of the material is on a phase boundary where it does not know into which of a Wurtzite phase it belongs. Now, pressure quenching, that's the right way. Pressure quenching works this way. You take the cadmium sulfide and you take it up to in excess of 40 kilobars. And it turns into the sodium chloride phase. When you release the pressure, some of the sodium chloride phase remains, but it remains in a matrix of Wurtzite and zinc blende. And it's the Wurtzite phase here which is unstable. I guess people have flashed things on before, so let me flash that on. This is what it looks like after pressure quenching. And this is some of the magnetic susceptibility data that we obtained at 77K, where we succeeded in obtaining at most about 1/10 of Meissner exclusion. Now, at this conference, this view graph is really unimportant, but this is the publication in which we asked the question, was there superconductivity at 77K in 1980? And perhaps after this conference we can cross off the question mark. Now, unfortunately, the microstructure that resulted precluded us ever measuring zero resistance. And our specimen looks like little platelets like this inside the Wurtzite matrix. But we were able to show measurements such as these, where on the same specimen and simultaneously we measured a collapse of the exclusion, penetration of the flux, and electrical changes that were consistent with superconducting regions becoming normal. How high did we see? What is this large diamagnetism? Here is an example which is a Meissner effect. We have a magnetic field of 1 kilogauss, and we're heating the specimen up, and it's becoming more and more diamagnetic, and at this point it switches from diamagnetic to paramagnetic, and we would argue that we see a TC of 170. In the paramagnetic state, we get behavior that looks like this. And I believe this is something which is kind of unique to this system and may well be found in some of the perovskite systems at higher temperatures. And then finally, our evidence for the metastable Wurtzite phase is this, that doping it with chlorine, we find that the lattice parameters show a discontinuity at exactly 0.78% chlorine. And what we believe is that when the pressure is released, the sodium chloride phase tries to become Wurtzite. It doesn't know whether it belongs in this phase or this phase, and there are a large number of soft phonons present. Thank you.
Thank you.